about En, which stands for what?
It's like electronegativity.
Electronegativity. And Ea?
Electron affinity.
Electron affinity. So tell me about electronegativity. Okay? I have these things over here. Which of these would you use to talk about, would you use this or would you use this to talk about electronegativity? Okay? Why are you going to use this to talk about electronegativity? Tell me. You said here is more En, electronegativity, right? What does that mean for this, the electrons? It would move here, and then what kind of charge would you have here and here? If the electrons are moving more here, right? Here would have a little bit of a minus charge, and here would have a little bit. So then this entire molecule, what do you call that type of molecule where you have a positive side and a negative side?
Yeah.
Polar molecule, right?
Yeah.
Right? So then here would you also have a polar molecule? Here. Yeah, you will also have, because this also, yes, this also has a lot of electronegativity, right? Negative and positive, right? But which one is more polar? This one or this one? Okay, and now, why? Right, fluorine has more En, electronegativity. And this is what you have shown me here. That if you go across this period of the periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, that the En increases, right? And why is the En increasing? You have it in your diagram, right? Two things are happening. Well, one thing is staying constant, and another thing is changing. What is staying constant as you go across? Look at it. 2, 1, 2, 2, 2, 3, and you go down to 2, 7. What's staying constant every time? The 2 in the front, and there are no numbers after this, right? Which means that you only have 2 energy levels. But inside the nucleus, what's increasing? Protons. Protons, what charge?
Photon is positive.
Yes, positive. And they're going to attract the electrons on the outside. So the more protons you have, and remember you're not putting in any more shells to block, right? So then by the time you get here, you have so many protons to hold these electrons. So it holds it very strongly. So this fluorine holds on to its electrons very strongly. But electronegativity doesn't really come out when something is a single atom, it's in a bond. When it's in a bond and you have something like this that's very electronegative, what does it do in the bond? It makes it polar. So therefore, which of these two is more polar? Right. And what about if I put H with Br? Right, it's always this one, because this is also polar, because this is quite electronegative. All of these belong to the halogens. Okay? So what about if I had even O and H and H? Electrons are going to be here as well. Right, so the most electronegative element, fluorine. Then the second most electronegative element is what? Oxygen is correct, yes. And the third most electronegative element? Not here.
Nitrogen.
Nitrogen. And there's something special because these three are the most electronegative. When they form bonds, these bonds are very polar. They're so polar that we put them in a special category. What do you call that type of bond? Where one molecule that has, like this, right, HF, with its negative charge here, and another H with a positive here. And the bond forms here. What do you call that type of bond? Hydrogen bonding. Right? So that's your hydrogen bonding. So all of this has to do with electronegativity. Now, with the other thing we want to do is to show how electronegativity is different from electron affinity. Yes, Abhijam?
When you say something has like an electronegativity of 0.7, like 4.0, what do they mean then?
Well, it's a relative scale. There's no unit, right?
Yeah.
So it's a unitless scale of which fluorine has the highest value of 4.
No, like how do you get that? Like what is it relative to, like to a certain?
Well, it's a measure. What is electronegativity? It's going to be able to define it then. It's a measure of the tendency of an atom to keep electrons closer to itself in a covalent bond. To say it's a shared covalent bond would be redundant because a covalent bond is sharing.
Yeah.
So the tendency of an atom to attract electrons to itself in a covalent bond, and fluorine has the highest tendency of all the elements in the periodic table to do that. Yes, Valika?
Is all the elements compared to fluorine to get the values?
I haven't looked that up to know officially if that is it, but fluorine doesn't have a unit.
Yeah.
Electronegativity doesn't have a unit. So is it all relative like atomic mass?
Yes.
I don't know if it's that. That's a good question though. That's a good question, so we should find out. But it's just a scale without any units. We also need to talk about electron affinity. Amount of energy when 1 mole of atoms from an element in the gas state receives 1 electron to form 1 mole of ions also in the gas state. That is, but that is the first electron affinity actually. There can be a second electron affinity, a third electron affinity, right? So that's the first. This electron affinity, is it exothermic or is it endothermic? It's exothermic because it's making this bond here. You are adding this in, and there's a strong attraction for this, so energy is released. But when you try to do electron affinity for something like this, what you have to do is you have to force this electron into something that has a tendency to want to lose an electron, right? And therefore it needs energy. And this is where I think the bond making and bond breaking thing would not work out. Because we always say that bond making does what? But isn't this making a bond here that you are putting a new electron in with sodium that has 1?
Yeah.
You are putting a second one in. But you are putting in a second one where another one, where it doesn't want the second one, it actually wants to lose 1. So energy has to be put in. And generally for these exothermic and endothermic reactions, we say bond breaking requires energy and bond making releases energy. But this is where students would sometimes get confused when you see that you have oxygen, it receives an electron, and it forms O negative, right, Abhinav? And
It's minus 141.
right, it's minus, that first one is minus 141, it's negative. But then you take O negative, you know this, and you want to add an electron to that. And then you see this.
It spikes up, it's like plus 700.
So in both cases, you are making bonds. You are actually taking an electron and bonding it to this thing. But in the first one, it's exothermic because it's easy for oxygen to acquire that first electron. But the second one, as it comes in, actually there's repulsion between the first one and the second one. And that requires extra energy from the surroundings. So this is exothermic and this is endothermic. What we also see is that you can take a topic from this topic that Lukyi brought for us. It's electronegativity and electron affinity. It's, I think, what chapter? Chapter 2 or 3?
2, 3.
Topic 3 is where we actually get it introduced. But then it's feeding into topic 4. It's feeding into topic 5. Because that's where it's feeding into topic 15, where you go into a Born-Haber cycle and you're seeing this. Try to see the big picture in your chemistry. And the thing is, now is the time to see it. Because it's only when you've laid out all the pieces of the jigsaw puzzle on the table and you've turned them over and you start putting some of them together and you make the corners of the jigsaw, then all of the pieces begin to fall into place. So even things that were difficult and boring for you in the beginning, now that you've seen the big picture, you can go back to them. And between now and the May exam, it's so much work that can be done. Also, your brains have actually grown, in case you didn't know. You guys are still growing. Your brains have grown. You have become more mature. And in addition to that, you have seen the big picture now, hopefully. So a lot of progress can be made. And this is not a time just to relax and do nothing. You can make a lot of progress between now and the May exams.